Okay, hello everyone. It is my pleasure to introduce our speaker today, Pia Bideau. Pia is currently a postdoctoral researcher at the TU Berlin, and she is a member of the robotics group of Oliver Brock. She is also part of the Science of Intelligence Excellence Cluster. And before joining the TU Berlin, Pia did her master's in electrical engineering and information technology at the Ruhr University in Bochum. Afterwards, she did a PhD at the University of Massachusetts in Amherst in the US under Eric Learned Miller. And in her research career, Pia has focused extensively on motion perception. For example, in her PhD thesis, she has worked on identifying moving objects from video streams with a focus on deformable objects like people or animals. And her current research involves mostly around event-based perception, which will also be a substantial part of her talk today. And I would say that perception is really, one of the most difficult and also most essential parts of a robotic system. And I'm therefore really looking forward to her talk, and I'm happy that she has accepted our invitation. Please welcome Pia Bideau.
Well, thank you very much for having me. Yes, my plan for today was to briefly talk about my PhD thesis on a very high level, and then in more detail on the most recent work on event-based cameras, which is basically both are connecting motion and different representations on how one can represent motion, and then later post-processes for higher level tasks. So I'll share my screen. Can you see my screen?
Yes, perfect.
And me not anymore, I guess.
I guess so.
Okay. Yes. So I will first talk about actually why is motion interesting, and why do we care about movement, and what can it tell us for the environment basically we are moving in. Then there are different ways how we can represent motion. What I just said, which is one is optical flow, which is currently, I would say, the most common representation on computer vision, but also comes with well, it's very accurate, but it also has many drawbacks, mainly in a sense of efficiency and computation time. And then there's event data, which is on the very opposite side, also capturing motion information, and in particular brightness, and is very, very fast in time. So here is now a video. It should be a video. Oops. Why is this video not playing? So, well, now it moved already before, so I actually wanted to ask you what you can see. And well, if nothing is moving, you cannot see too much in this video. But as soon as an object starts to move here, you can clearly see the stick insect, which is moving, even though the appearance is very similar to the background. And here's the other example. You can see a house. This is a static scene, but if you start moving, I guess it's the internet which is slow. I know. sequence. Here you basically can see that you can just extract the depth and the scene structure just because you yourself are moving. And first it looks like a normal house in 3D, and then you can see that it's just flat and a flat surface with a weird structure. Now stop this video. So Gibson was, I would say, one of the first and who studied a lot motion perception and especially structural patterns that you can find based on brightness changes. And one of his saying that I like very much is, we see because we move, and we move because we see. And if you want, this also connects basically on the one hand, the perception and the action side, but which is actually very connected to each other. And I'm not even sure whether you can disentangle those both sides. I've learned about this while I was starting with roboticists, about this very strong connection or separation, which is right now trying to get together, basically. Yes, so the two forms of motion, and I don't know so much how much you have heard about it. So one is the optical flow. So you have a motion field, and at each pixel location, you have a vector pointing into the direction where the pixel will go to in the next frame. Event data is more sparse and captures just brightness changes at pixel locations wherever the brightness changes. So you do not have any grid like a frame or picture we are usually used to. The basic underlying idea about optical flow is the brightness constancy, that one point in the world does not change its brightness. So we assume that the light is constant, no switching on, off, turning on the light or something like this. And then while the camera is moving or while objects are moving, these points are displaced on the image plane and create a motion field that you can see here on the right with the color pattern. And you have basically the color encodes the direction and the magnitudes encode the, well, the magnitude is encoded by the brightness in this color scheme. Intense colors have large magnitudes and brighter colors have small magnitudes. And what you can do a lot of things with optical flow, and this is a very important representation in computer vision. So I've been working on motion segmentation, and recent approaches, basically they are learning-based approaches for motion segmentation that take optical flow as it is, as input, and try to learn the motion patterns that you can see, because also without any pre-processing or understanding in geometrical structure, one can see a person here or the flamingo. Other works used optical flow and more tried to cluster then different motion patterns, which are sometimes then leading also into depth-dependent segmentations, like you can see here in the ladder, where parts that are close to the camera and lead to larger displacements are grouped together, which is not necessarily what we want. And a brief overview about event cameras. So these are very fast and it's basically high dynamic vision sensor that do not capture frames as we are used to. They only capture the changes in brightness at each pixel location. And on the right, you can see a event stream, basically. The blue and red dots are like positive events or negative events, which encode a change in brightness going from light to dark or from dark to light. The black part I just plotted to show to give you a little bit of an idea about what scene is recorded. It's a projection of the events on a 2D plane. But of course, you use all the temporal resolution if you do this. So this is a more schematic view of event data. So you have a scene on the left with the violet points. You have the scene at points where the brightness changes. In black, you have the sensor of the camera, which is moving here upwards and is recording the brightness changes. So while the camera is moving upwards, brightness changes are triggering events on this camera sensor at different rates. So the faster the motion of the camera, or also the stronger the brightness change, the higher the rate of the events that are triggered. So here in the beginning, so you can see at the beginning the red circles are triggered at a very high rate because the camera is moving fast. Then the rate decreases because of a slower movement. The stars are at lower rate in general because the brightness change is not so much between the two gray values than the white to the gray. Well, work in event-based cameras, they are trying to get some information of this asynchronous event streams, basically one way. And Guillermo here at TU Berlin is one of the specialists and actually derived this method, which is contrast maximization. You try to align events to get very sharp images. So on the left side, when you project all the events to a 2D plane, you create an image, which is very blurry, and then you want to transform the events to create a sharp image as on the right. And based on this, you could also do motion segmentation, which was a follow-up work of him, where you basically align motion clusters and try to enhance the contrast for each cluster of the event stream. This is a brief overview about event camera and optical flow. So event data really just records brightness changes, whereas optical flow really already makes the correspondence between pixels and is thus much easier to interpret, I would say, and also to extract structure of the scene. Optical flow, however, is estimated from RGB frames, so there is a pre-processing step which is needed and makes it much more inefficient in terms of time. So this about the background, about the motion. Any questions in the middle? Or I just continue? And I just continue. So I think I won't go in too many details into the PhD in my PhD work, but give you an overview. So my idea really was that I would like to learn motion patterns or motion segmentation from optical flow, while also keeping the information about scene structure, such as depth and camera motion in the loop of the estimation procedure. I've been studying with two very probabilistic approaches, and the last one also kept the structure basically of my earlier work, but then used a neural network basically to learn motion segmentation masks. So I will talk about the very high level idea here, where all three approaches are based on. So therefore we need to understand how a motion field can look like. So here you have a goat, you have like motion of the foreground and background. And essentially, if it would be a little slower, you can see that even the foreground pixels move into the different direction than the background. So to correctly estimate the motion, you really have to disentangle the camera motion and according to the depth. Next. So how does optic flow look like? So in case we have no camera motion, it's relatively easy because all pixel displacements directly correspond to the moving object, and you could just segment or do background subtraction to get the moving object. If we have now no moving object and only a moving camera, this is a rotation, we have a very simple flow field where everything just moves into the same direction with a very similar amount of motion. If the camera is just translating, the translational field is depth dependent. So we have a large displacement close to the camera and just very small displacements for areas that are far away. Now, if we put both together, this makes the motion field complicated because now we have camera rotation and translation, and part of the image moves into one direction on the 2D image plane and the other into the other direction. So I need to understand basically the camera motion to be able to understand that actually nothing is moving here. Well, and then I have the object motion, and now I have 3 different motion clusters basically that I want to correctly segment. So the key idea of the approach is basically that I'm segmenting optical flow based on the angle or based on the direction at each pixel. If I have rotation and translation together, the angle in the optical flow is very dependent upon the scene depth. However, if I subtract off the rotation and compensate the flow field for the rotation, it's basically kind of stabilizing the motion field, or what we do with our eyes when we move, we compensate also for our motion fields. If we have a translation field only, then the angle is independent upon the depth. And I get a very clear angle field which I can assign a translational motion to, and then I have moving objects that basically stand out. So this is the high-level overview. So I will start with picture A here on the left. So I have an input video sequence here. This are 2 frames, and optical flow is computed based on 2 frames. I'm getting an estimate of the motion field here, the optical flow in B. I'm estimating the camera rotation, also here just based from optical flow. I subtract off the camera rotation and get a rotation compensated flow field in D. And then I only look into the angle in E. And the angle field now is easier to segment in terms of motion, because the tree, which was standing out before in the flow field, is now, you can see now that it's actually moving in the exact same direction as all the other flow vectors. Only the human here moves into a different direction. In black and white, in F, but you cannot see the figure, you can see the magnitude of the flow, which is also an helpful information, but not so much to decide what is moving or not. It is interesting, though, to decide how much information each flow vector has. So if I have a low magnitude here, like in the focus of expansion, the vectors are much more noisy and are thus not so reliable to decide whether they point into a different direction because those are moving, or the flow vectors are just small. As I said in my last work, this part on the bottom kind of changed, and I worked a lot of this in my PhD. And it was first a probabilistic model, then I had a UNet network where I basically tried to learn, keeping basically the physical structure of how the optical flow field is constructed, with having flow due to camera motion, due to depth, and due to object motion. Then having as input only the angle field together with the magnitude to learn basically the motion pattern here on moving object on the left, which is the figure J.
Can I ask a question, Pia?
Yes.
Just one thing I'm pondering. So I think you assume that there is a camera motion and the object motion, right?
Mm-hmm.
And the camera motion leads to many pixels to move. Mm-hmm. But is it always the case that then all these many pixels move in the same direction? So you explained with the tree. I mean, the tree moves a lot more than the background, but it moves in the same direction. And that's why in the angle field, in the angle view, it's in the same direction. But is this always the case that when the camera moves, that all pixels move in the same direction?
Into the same 3D direction. So here in E, you have the camera motion, which is a Z motion, because you have this rainbow pattern.
Yeah.
So it's not that when I say into the same direction that everything moves to the right. So at each pixel location, they move into the same direction according to the 3D camera translation. Is understandable?
Okay. Yeah.
So here it is basically a Z motion with maybe a little bit of X motion to the right. So the focus alpha expansion is here on the right. And yeah, so the flow pattern is the angle is very consistent and can be, looks always the same if there is no camera rotation.
So you're saying,
But I do have to subtract of the camera rotation. Otherwise, I get this difficult combination, what I showed with the goat image, basically, where sometimes just because of depth, pixels move into other directions.
So I see.
Here the direction is only determined by the translation.
Yeah, I see.
And I don't have influences anymore of depth.
And if the focus of that movement would be exactly on the human, then that'd be pretty messy around the human, right?
Yeah.
Okay, I got it. That's nice.
Yeah. And then, well, because I then know really the structure of this flow, like in E, and I can really define, I know the background moves this way, and I don't have the figures now for that in this slide, but because Mark is asking. And basically the moving object is just a connected region moving into another way, into another direction. I trained the network or pre-trained the network basically with data that I synthetically created, because I can create just synthetically a background motion, a translational field. Then I can have a connected region somewhere that is moving into a different direction, and train the network to learn this structure a flow field has when I have subtracted the camera rotation. Yep. So this is already about the approach of my my PhD. And when I evaluate such an approach, we compute the intersection over union. So the intersection between ground truth and my estimation, and the union of both. And here are some results for that on a data set that we typically use in computer vision. It's called the Davis data set, which has just moving objects, moving camera that are moving. These are 50 videos. And Tokmakov et al., this is a method that do not decompose the optical flow into basically camera rotation and translation to do the segmentation. They directly estimate the flow from the optical flow field. our approach, our flow, shows that we do get a little improvement by basically disentangling this camera rotation and structure. With our flow ground truth mask, what I tried there is there's always a little error when I estimate the camera rotation based on the anti-optical flow field and I don't know what's moving. So the motion of the object, of course, disturbs a little bit the estimation of the camera rotation. So I'm using the ground truth masks here of the data set to estimate the camera motion and then do the motion segmentation. So this shows me how much improvement I could get when my camera rotation would be better and not be corrupted by moving objects. So here's a failure case of our approach, which is a little difficult. So here we have I just show the translational flow field. And in this case, it's actually very hard to decide what's moving because the background, the flow vectors are so small and it's very noisy, as you can see here in the angle field. And one could say the camera is just static and we actually might have a moving object here in the foreground and the cars are moving. So maybe these are 3 different moving objects. Or we do have a camera motion and we have depth difference. Then the foreground, this wall would be assigned to be static. But in this case, it was not correctly segmented basically and assumed to be a static camera such that the foreground here was moving. Here's some examples that it also works well. I feel like somehow the videos, due to the internet connection, well, this is dog, worked. I hope you just believe me that it looks good. Okay, the car. Well, these are some examples of the Davis dataset where we evaluated our method on.
Just to check, so basically this is one network that you trained that always works, right? Meaning, so here in all of these 4 cases, it's always the same network, right?
Yes, yes.
And it should basically always work and pick out. And what would you do if there is 2 objects moving?
It would not basically distinguish whether there are 2 moving objects or not. It would be just a binary segmentation here.
But it would then like show you 2 blobs, right?
Yes, show me 2 blobs.
That's good.
Yeah.
Okay.
One could add then maybe an object segmentation or semantic segmentation approach to split those. Mm. But yeah, it's just binary, moving or static. Mm-hmm. Oops. So then I would move on to my last work on event data. If there are no more questions right now for optical flow, but of course later optical flow questions are welcome too. Okay. This is a much more probabilistic and hopefully good, understandable approach. So I've just submitted it on arXiv last week. So the goal here is basically to align also the events while also estimating the rotational velocity of the camera that lead basically to the disturbance of the events on the pixel plane. So again, so how are events triggered? And I said this a little bit earlier. It's basically the rate at which events occur are triggered by the image gradient at a particular pixel and the motion field vector. So if I have motion just parallel to an edge, no events are triggered. If it's orthogonal to an edge, events are created at a very high rate. And also, the stronger the image gradient, the stronger the rate at that events occur. Yeah, and so the goal here is that we would like to find a transformation that converts a set of events to the most likely set of latent events. So the idea of latent events, basically that each event is triggered by the same location in the 3D world. So we would like to align all the events that originated from the same location, but occur then on the sensor at different pixel locations. So the idea of alignment comes actually from earlier work of my PhD supervisor, Eric. He has done his PhD also on image alignment, and he developed congealing, which is about that you want to minimize the entropy along a pixel stack. So if you have binary images, like here on the left, you want to transform each image such that the entropy along this pixel stack is minimal. So ideally, all are black or all are white. And now with events, I would actually like to do something similar and have all positive events and all negative events also lined up at one pixel location. The problem is just that I don't have images, which are binary. I have events, so I need a different model that leads to an alignment. So here's again the goal. So I have on the left the observed events, what I showed before, and the goal is basically to move to the right side where all events that come from the same location in the image are well aligned. And how the new thing in this work is basically that we model these points. Well, I will talk about this later. So basically, we want to align the observed events here on the right to get to aligned events on the left, to get to aligned events on the right, while also estimating the camera rotational velocity. And for that, we developed a likelihood function, which for the aligned events, that measures how good our events are basically aligned at one pixel location. The underlying idea here is that we model an event as a Poisson point process with some rate parameter that we do not know from the beginning. But this rate parameter depends upon, as I said before, from the brightness or also the movement of the camera. So basically the probability of observing k events can be modeled with the Poisson distribution of k given lambda. So now there's a little bit of math. So to compute basically now the probability of k, and I don't know the rate at that events are occurring, I integrate over the rate, and then yes, I integrate over the unknown parameter lambda, and then use Bayes rule basically to have a likelihood function of P of k given lambda? What is the probability of observing k events with a known lambda? And what is the prior, which is the prior over lambda? So on the left, you can see how Poisson distributions look like for different lambdas. And for the prior, we measured basically the distribution of lambda on event data and found out and could fit basically that it's looking very similar to a gamma distribution. So we have many pixel locations that have 0 events, so the rate is low, and a few pixel locations where we observe up to maybe 6 and some 8 events, always, of course, within a batch of events. Yeah, and this then led to the gamma distribution. This goes into much more math, but it's actually not so complicated because there's the gamma Poisson mixture model, which facilitates everything and leads basically that the probability of k events is nothing different than a negative binomial distribution, which is much easier to compute. So our optimization function is basically optimizing the probability P of A of the events that are transformed according to a rotational velocity of the camera. This was now a little bit math. I hope most of you could follow somehow, but now I will show some results. So this appeared to be a very robust and good approach, basically. So Cmax is contrast maximization, which is currently the most known and used method, I would say, to align events.
Can I ask, before you explain the results, so what we optimize for the decision variable is the movement of the camera?
Yes.
Did you say that?
Is the angular velocity of the camera.
And the difference between all these methods actually is just the objective function, right? So the measure of consistency of the seen events. That's,
yes.
Okay.
Yes.
Just
so Cmax basically computes an image of warped events. So everybody here is considering a fixed batch of events, like 30,000 events. It's not that great, I would say, for event cameras to consider a fixed batch of events, but one needs to improve and work on that, I would say. So everybody used 30,000 events. Contrast maximization simply computes the contrast of the image when you accumulate all events to a 2D image, and then you want to transform the events such that in the end you ideally have sharp images, so an image with a high contrast. We have this probabilistic model with modeling the events as a Poisson point process, which apparently I think is more robust to noise, which is also very happening a lot in these camera sensors. Yeah, so much maybe just to the numbers. We have computed the speed. Contrast maximization is still the fastest and the most efficient one to compute. We are a little bit slower. The entropy minimization is incredibly slow because they connect the connections between each event from one event to each other event and try to minimize the entropy and the distance between all the events to each other. And computing the distances from one event to all the others is just super expensive. Here are some images of sharp images. So you have the original image here. The first line, you can see actually Guillermo, he's in the data set. And And you have the unaligned images that are just as recorded from the event camera, and the results of Cmax. This is the approximate entropy minimization objective function, and in the end you have hours. What you can see is that the first 3 lines are actually all working pretty well in terms of alignment visually. On the last row, which is actually the simplest scene, we still have blurred images. And one reason here is that we have a fixed batch of 30,000 events. Because this scene is so simple, we have very clear brightness structures, and not so many events are actually triggered in the same time interval. So the batch size, 30,000 events, highly depends upon how fast is the camera and also how does the scene look like. If I don't have so many events, the alignment gets difficult. If I have too many events, the alignment is also difficult, because you cannot simply align everything with a single rotation, with linear consistent rotation. So here we basically showed how the batch size of events influences the accuracy. You can see that for the shape sequence, much smaller sets of events would be much better. Whereas for the others, like event size of from 20,000 to 40,000 work all pretty well. There are some other methods that try to estimate how many events are optimal in one batch size, but here for comparability, we just set the event size. Same for all methods. Yes, and on the right, you can see how images look like with different sizes, different amounts of events. They are not aligned here. And one basically suggestion or idea how one could even more improve is not assuming a constant velocity within one batch, where you can see in figure E, where we assume a constant velocity and align all events according to that. It would be much better to have an affine velocity model where the velocity can change linear in one batch. And this would actually lead to much better event alignment, but people are currently not doing it. And we didn't do it too, but we showed some examples that this is a good strategy or a nice idea to do in future, and to also account basically for the high speed of the camera and evaluate then also with high speed. So this was then work with a master student here at TU Berlin that I supervised, and with my former PhD advisor, because he was just so much involved into congealing, and another professor also at UMS who is more into statistics, Guillermo, who had the background in event cameras, and me as a postdoc leading this project. So this was a big project group, and I think we developed a nice new model for events, and the code is also available. So in case you use events, just try it out. That was it from my side. And this is just an overview again that I had before about the difference between optical flow and event data for different motion representations. Thank you.
Yeah, thank you.